So for the recording, for the record, I would like to welcome you once again. And today, as a speaker of the quantum computing seminar, we have Tomasz Śmierzchalski. No, no, not correct.
Śmierzchalski.
Yeah, that's the correct pronunciation. He's a PhD student in fourth year of his PhD studies in at Institute of Theoretical and Applied Physics, Informatics, Applied Informatics, sorry, within the Polish Academy of Science. Yeah, and yeah, I think I will give him the microphone, and it will be the best thing to do.
Hello, everyone, and thank you for having me here. In the seminar, I will tell you about the limitation of tensor network approaches for optimization and sampling for comparing to Ising, classical and quantum Ising machines. So the title is quite a mouthful, and we will go by it step by step. Here is the basic outline of this presentation. And I had the idea that or maybe I will ask, is someone here like familiar with quantum annealing or tensor network methods? Okay, good. Because I thought that I will use this presentation as the opportunity to introduce this concept and give some taste, some bite-sized taste about these methods and quantum annealing and how it look like. So first, I will give you the brief introduction to the tensor networks, like really brief, just do really basic stuff. Then I will introduce the problem, that is the why we care about this Ising optimization, what is quantum annealing, etc. All this background stuff. Then I will introduce and show a method we have developed, the SpinGlassPEPS algorithm. Then I will show you some benchmarking results. And also, I will show you the short demo and tutorial how to use our software we have developed for your own needs. So let's start about tensor networks. First of all, as all mathematicians here know, the tensor is just a multilinear transformation between linear spaces and collinear spaces, but we don't need to go to such detail. For our needs, the tensor is just some set of number, which is indices, which is labeled by n indices. With n, n we call the order of the tensor. And I give a little star here because in some literature, it is called the rank of the tensor, not the order. So it really depends on the author, which one they like best. And here's the example. The first order tensor is just the vector, because we have one indices, which we can label it. The matrix is the second order tensor, because we have two indices, and like this three-dimensional cube of number, like here is a third order tensor, because we need three indices to label it, etc., up to the n. So when you have tensor, we need to do something with them. And the most basic operation with tensor networks is called index contraction, where the index contraction is just the sum over the all possible values given index can have. And in my experience, it is best to show it on the simple example, matrix multiplication. Generally, to obtain any, when we are multiplying matrices to any number of for the resulting matrix is just the sum over like these two numbers. And we are contracting it by the index j here. And mathematically, that is just the index contraction, this sum. And of course, we can have much more complicated examples. As we can see that we have several third-order tensors that we are contracting with by all of their indices. And at the end, we have just some number. Okay, but this notation, it is quite hard. Some terminology, because we go here, the indices that are not contracted. Here is some other example. And indices that are not contracted, that is, indices that are left, are called open indices. The contracted indices are often called bond indices. And this terminology comes from the many-body quantum physics. But I will go to there. And the number of possible values that given indice can take is called the bond dimension. And the biggest number of that is also called the bond dimension of the whole operation. So all this notation is quite hard and not very useful. So here, I want you to introduce the diagrammatic notation or graphical notation, in which tensors are represented by some shape. Often it is some circle or square or triangle, whatever you like. The shape itself has no meaning. And each, like a line that is going from this shape, also in the literature called the leg or little leg, coming, is an open indices. So the scalar is just some shape. The vector, here we have some tensor with one open indices. Here we have matrix with two, and third order tensor with three, etc. And also in the literature, you can find that people want to introduce, like, if there is a triangle, it means that we have some tensor, etc. But in general, the shape and the direction of the lines does not matter in general. But some authors like to introduce, to give some meaning to that. Okay, but why we would introduce such notation? Because it makes index contraction really easy to see. Example here, it is matrix multiplication. And we are contracting by index j. That way we are like gluing these two tensors together, and at the end we get another matrix. And here we also can easily graphically see that this notation allows us, like, the contraction of two matrices is still a matrix, etc. And for example, here is the second example. From now, it is easy to see that it will be just some number because there is no open indices. Okay, so far so good, because now we will go to some harder stuff. So I introduce the tensors, I introduce what to do with them, and then I can introduce the tensor network. In principle, tensor network is just some set of tensors with indices and some special way of contracting it. And this definition is really, really general, and it serves a purpose because there are many, many different families, useful families of tensor networks. But I will go to them in the due time. But first of all, I want to stress some very important property of tensor networks. That is, the number of operations we have to do depends heavily on in which way we are contracting it. Because in general, the number of operation is like O to the D, or D is a bond dimension, but it really depends on the way which way we will contract the tensor network. And it is important, and I will go to that later. And second, what is the purpose? Generally, I won't go into the details how to do it, but in general, tensor networks can be used to break complex systems, for example, wave function, partition functions, into smaller, more manageable pieces. And that is their main role that we use them. Okay, next I will give you some examples, families of tensor networks, starting with matrix product state, or MPS. In general, MPS is just the one-dimensional chain of the tensors, connected tensors, in which each of them has one open index. And here is an open boundary condition, but we can also have closed boundary when this tensor will be connected to this one. So, in general, MPS, or also known as tensor train in the mathematical community, are basis for many powerful algorithms for one-dimensional quantum many-body systems. For example, DMRG, that is density matrix normalization groups, time estimation, TABD, I forgot how this shortcut works, but they're really useful. And what is important, the MPS are dense. What does it mean? That with sufficiently high bond dimension here, it can represent exactly arbitrary or any state of many-body Hilbert space, which is really useful property. And also maybe one of the reasons why it's so powerful and basis of so many methods. And the second, and the tensor network family, which we are actually using in our method, which we'll go to that, is the projected entangled pair state, or PEPS. It is just natural generalization of MPS to the higher dimensions. And it can also, as MPS is good for one, but many of these properties are like going through. So it also can, with sufficiently large bond dimension, represent any many-body two-dimensional quantum state, etc. But, oh, there's an error here, because because in general, contracting the PEPs is P-sharp hard. That means it is harder than NP in general, because the sharp P problems are accounting problems, and I don't know if you are interested in the complexity theory here, but it's useful to know that it is harder than NP problem in general. So that's why there are many methods to like heuristically contract them. Okay, so for now, and if you are interested in tensor networks, I can just, because it was like really fast, really brief introduction, we can easily take the whole course on the just introducing the tensor networks methods. And I can recommend really good papers here, one by Orus, which is really written with, simply written, but really rigorous and gives great introduction to like the whole field. And also the book, Tensor for Contractions and Applications for Many-Body Systems. It is a great book. Like, and I can wholeheartedly recommend it. And also it's a lot bigger and go into the lot of the details here. And other very useful resource is just Tensor Network, which is just website with many like introductory papers, more advanced papers, methods, like great resource of information, and just TensorNet, which is more on the applied side, with many great tutorials on how to program them in the Python, MATLAB, or Julia. Okay, so now this introductory, so far so good, introductory stuff. It was like the briefest of brief introductions. But just to introduce the notation, just to introduce this graphical notation, which I will be using for the whole presentation. Okay, so now we can go to the problem, why we are using these tensor networks and how it goes. So we are interested in this optimization problem that is defining the ground state of the classical Ising model, which is shown here. And maybe it doesn't look so scary because there are just two sums. But what is important, the connectivity structure, we assume any arbitrary graph we can use, and the h and j's for like each edge and each node can take any values. Because that is the idea. We have some graph in which we label edges and nodes, and we try to minimize this sum so that the solution, like with this spin vector with +1 and -1. That is, and it is understood what we want to do here. Find the spin vector plus or -1, ones that are minimizing this sum. Okay, but what do we care about some two arbitrary sums, etc. So first of all, finding the ground state of the arbitrary connectivity with Ising models, with these arbitrary couplings and external fields, this arbitrary J's and H, is NP hard problem. What does it mean? That means that many important problems in computer science, physics, can be expressed in the form of some Ising model. And I mean many, like traveling salesman, protein folding, max cut, optimizing stock market portfolios, etc. Generally, to be precise, problem is NP hard if any problem in NP can be in the polynomial time reduced to this problem. And it is shown there are like almost every NP problem can be, no, all NP problems can be expressed as some Ising model. And also, it being NP hard, it implies that only method to be guaranteed to find the solution, that is to find the lowest, to find the ground state of the lowest energy, is via brute force. That is to check each possibility, which is like to the n possibilities, where n is the number of spins. And as we can see, it is growing exponentially and quickly becoming infeasible. And second of all, because this is such an important problem, there are many different heuristics, classical and quantum algorithms for solving this problem, including purpose-built machines such as quantum annealers. Because quantum annealers, what they are? There are some physical machines that are implementing quantum annealing algorithm. But to be precise, there are machines built to solve the Ising problem using adiabatic quantum computation. And now I want to stop for the little and introduce how the quantum annealing works. In general, I don't know if there are any physicists here. No, okay. So I will go the mathematician's way. But the idea here is that if we start, is that we have some system that is composed of the two Hamiltonians, which we call initial Hamiltonian and final Hamiltonian, where the Hamiltonian is some function that is mapping states to the energies. So the idea is here that we have these two steering function A and B, which are depending on time, because here S we called S as normalized time. And the idea here is that we are evolving the system really slowly. And on the start of the evolution, the A is really big and B is almost zero or really small. So we are starting in because this is sigma X Pauli matrix, we are stating in like really maximum quantum state. Because the ground state of this system is just everything is in the superposition. So we start with the quantum state. And then when we are evolving the system, A is going down, B is going up. So that at the end of the evolution, this part disappears and we are left only in this part. And then we are go to the important thing, that is the adiabatic theorem of quantum mechanics, which tells us, in principle, if we start in the ground state of this Hamiltonian and evolve it slowly enough to this Hamiltonian, we end up in the ground state of this Hamiltonian. That is the basis how quantum annealers work and how they are solving the Ising problem. But what is important part is that they cannot solve an arbitrary Ising problem. That is the non-zero values of H and J's here, or the values we are taking to the edges and the nodes, are limited by those available to the working graph. That means we are limited by the connectivity structure of the quantum processing unit that is on the machine itself. And here I am presenting the small parts of these graphs topologies. And here the nodes represent qubits and the edges represent couplers. That is, they are representing how the quantum processing unit is connected in the machine. And we have like two big families of QPUs called Pegasus and Zephyr, where Pegasus is current working topology and Zephyr is still experimental. But when it will be built, the full Zephyr will have 7,500 qubits and 70,000 couplers. So as we can see, there are quite big number of qubits. But I want to stress that this machine can work only for solving the Ising model. It is not a general quantum computer. And we cannot apply gates here. Only thing we can do is to evolve this state to find the ground state of some Ising model. So, okay. And when we are here now, and I want to stress that this connectivity is really limiting. I mean, there are like quite sparse graphs, but also dense enough that simulating them is a problem. And what idea did we have for our method? Generally, we have this idea that if we have Ising model, then the lowest energy state that we want to find, so the ground state, is also the most probable state when sampling from Boltzmann distribution, etc. So we can perform branch and bound search in the probability space. And how branch and bound algorithms works. I will describe it later in the great details, how we are implementing it. But the general idea is that instead of solving the whole problem, we are solving a bunch of smaller problems. The idea is that we start with an empty state with probability 1, and then we are calculating the conditional probability when solving for spin systems. Conditional probability of first spin going up or going down. Then, and this is called branching steps. that we are calculating two different solutions. And then we take another branching step, that is calculate what is the probability, control probability of spin going up, given the first spin was up, etc., etc. But it is easy to see that right now it's amount to nothing more than a brute force search, because we are searching all possible configurations. Then that's why we come to the bounding step. That is, bounding is such some function or some method to eliminate some branches in this tree, or to like throw away some solutions and don't go there. And here the idea is that we are just keeping m most probable solutions. And in this case, like only this three, and this fourth one is thrown away, and we are not looking for it into it. And then we go with another branching step, another bounding step, etc. That is the general idea of branch and bound. I will go into more. And in probability, and if we had a way to exactly calculate these probabilities, we would have guarantee to reach the ground state, because it is like working branch and bounding solution. But what is the problem? Calculating the marginal probabilities require sampling from the Boltzmann distribution, which is shown here, which is just e to the minus beta, which is some parameters, which we call inverse temperature, and the Hamiltonian, or the values of energy. But what is the problem? The problem is here with Z, where Z we call something that which is called the partition function. And it is just like the normalizing factor, which is just the sum over the all possible configurations. Here we calculate this factor for them. And that is really expensive to calculate, because we have exponential number of possible configurations, so we are screwed with that. But there is a solution to the problem. That is, we can use tensor networks to calculate or just approximate this partition function. And that was the general idea for creating the SpinGlassPEPS algorithm. That is, use this bound and bound search in probability space. We can perform it using tensor networks to approximate the partition function. And so we are able to calculate these conditional probabilities. And we want it to work on the connectivity structures of these modern day quantum annealers. That is the idea for our algorithm and our software. So first, and it consists of three main parts, or three problems we want to solve, or something like that. That is, which then later informed how we build our software. That is, we want to transform the Ising problem into some other thing that is more suitable for QPU graphs and tensor networks. Because if we try to build tensor network in the shape of the quantum annealing QPUs, also we would be dead there. We would achieve nothing. So first, we must transform this problem into some other which is more useful. Second, we must perform the main steps like branch and bound, find the low energy states, and sample. Because I want to stress something, that at the end of the branch and bound procedure, we not only get the most probable state, but in those states we are keeping n most probable states. That is, in fact, we are sampling from the low energy spectrum of these problems. And that's why we want to perform main sampling and search steps. And third one, we want our tensor network calculations to be efficient because the matrices there are becoming really large really quickly. Okay, so how did we solve these problems? And I want to ask, any questions for now about quant? Yes? Ah, okay. Okay, so now I will go to and introduce our tensor network approach. How we solve the first problem. And now it can be a little scary math. That is, we use generalized Potts Hamiltonian. What is that? It is some generalization of Ising Hamiltonian in which our variables can take more values, not only -1 and 1, but can take some arbitrary number of discrete values. So idea here is that we can group the spins together, the spin variables on the QPU graph or the Pegasus graph, and transform them into some, and group together, of course, the connection between them, and create some easier structure on the Potts Hamiltonian. The only problem now is that we have here the variables are quite big because each of these variables is can represent the configuration of the so-called unit cell. And here we have connections between them. But this connection now, the number here are not just some numbers, but they are matrices, which you can find here. And so we have this generalized Potts Hamiltonian where, given configuration, we are summing over first. Here there are so-called intra-node energy matrices. That is the energy of each configuration that can be found in this Potts variable, like here and here. And intra-node energy matrices, that is the energies of these lines. Here, the green lines represent diagonal connections and blue ones represent just standard square lattice. Okay, so that is our first idea, that we are grouping the spins from these architectures into these Potts variables. But also, we have met another problem. That is, these Potts variables, these xn's, this configuration, can take up to the 2 to the 24 for the Pegasus graph and 2 to the 16, it should be Zephyr here, for the Zephyr graph. That is because we have all the configuration in this unit cell, and here we have 24 spins, and here we have 8 spins. 16 spins, so we can 2 to the 16 or 2 to the 24 possible configurations. It is not nice. But we note what is important, that not every spin of each of these unit cells is connected to every other spin of the neighboring unit cells. So we can compress these variables. That is, we can compress the energy matrices which you are using. And also, what is more important, we can compress our variables by using projectors, which are projectors for linear algebra, which are just going from higher dimensional space to the lower dimensional space here. And the idea is here that we can compress the energy matrix to only include the existing connections. And also we can, when we have only these existing connections, we can compress this whole deconfigurations into the unique, here denoted by d to the power of mn, unique sub configurations. And here is how we do it graphically. That's why I told you that the tensor network graphs are important. As you can see, here we have one unit cell, second unit cell. But when using this big variables here, we can project them using projectors into the smaller space, and then only like calculate the energy matrices of the existing nodes, like the existing connections. And here is how it works for the Pegasus graph. That we have to the 24th here, but we can go like going up only to the 12, to the 18, etc. And this is how it works for the Zephyr graph. Okay, so we have some way to compress it and to represent the Ising problem into the something which is more like digestible to the tensor networks. Okay, so now we go to the bounds and bound step. And I hope that you can see from what is here on the slide. But what is the idea here? We are building our solution step by step, going from right side unit cell or pods variable, and going step by step here. Building our solution. How we do it? Here is the idea. We have like xn variable set, and we are adding xn plus 1. So first, we perform bounding step. So we are looking at each of the m possible configuration that we can get from here. We have first configuration, second configuration, etc. To the m possible configurations. Okay, that's the first step. We are branching. Sorry. Then we are calculating the conditional probabilities. Because I will use here this, as I will remind you, we are sampling from this Boltzmann distribution. And the idea is here, we are calculating the conditional probability, because if we want to calculate the probability of this new Potts variable or given configuration, we want to calculate the conditional probability here. So first of all, we start to calculating the conditional probability for each of these branched variables. But here we perform very important optimization. That it's here. That the conditional probability for a given configuration of the next variable depends only on its boundary of the previous system. That means not on the whole system, but only on the variables that are connected to it. Everything else doesn't matter, so we can really cut great number of configurations that we are considering. And that is very important. Here is the formal definition of the boundary, and that is the important step here. So that's how the branching works. We are calculating the conditional probability of every configuration in the new Potts variable, given the configuration we are keeping on the boundary of it. And then we are bounding, that is keeping only the m most probable configurations. That is the general idea of how our search and sampling works. It is quite complicated, but I still have time. Little joke, so I can go. Is so far so good, or are there any questions now? Not. Great. So how we calculate this probability? Because still, we still didn't solve this foundation basic problem. And here we go. As I said, we use tensor networks. And now I will tell you how we build them, this PEPS tensor network. Here is our Potts Hamiltonian with Potts variables and connections we have here. And it is translated into the PEPS tensor network with several different types of tensors. That is, the red one we called the side tensors. And they are representing the possible configuration of the given Potts variable and assigning calculating the probability of given configuration. It is represented here. All the squares are these energy matrices. And also with these, to be precise, with these side tensor, we are tracing by the given configuration. And here, as you can see, we have the connecting legs with the, here triangles means projectors. And one physical degree of freedom, which is here, which is open index, which is index representing our probabilities of a given configuration in the Potts variable. And this is just the trace over the intranode energy matrix with the projectors and this minus beta, which is thermal parameter for our search. Okay, so here is the triangles are projectors. And what is important also? These purple dots and green energy matrices are built in the special way to mediate the diagonal connections. Because the algorithm we are using for contracting PEPs doesn't allow us to use diagonal connection, we must go around it. And we do it by introducing these two additional tensors and this energy matrix, which is mediating it, this diagonal connection. So, and by contracting this tensor network, so by reducing it just to the one tensor, by summing over all values of the indices, we can get the partition probabilities of the partition functions for each of the configuration. I hope the general idea is understood. Okay, more or less. Yeah, more or less. The greater details are in the paper, which will be later presented. But I just want to give you a general idea that we are building. The main idea to take from here is that we are using different types of tensors that are doing different things. We have one type to mediate the diagonal connections. We have tensors for the energy matrices, which are mediating the internode energies in the Potts Hamiltonian, and we have side tensors for the for representing the probabilities and the configurations in the tensor network. That's the general idea I want you to have here. And how are we contracting and calculating these probabilities? As I said, when introducing the probability of the given configuration of the next variable depends only on the boundary of the tensor network. And so when we contract it, we are just taking the boundary here, which is represented by these gray squares or gray diamonds. And then we are contracting the rest of the tensor network using different approaches. We are implemented many different methods, but general idea here is called MPS boundary approach. That is, we are contracting the network step by step here, going these tensors with this matrix and here, and then this one here, this one here, etc., such a way that we can contract the whole network into these. No, just to this boundary and just for this one. And given that the probability only depends on the boundary, we can, like, for the rest of the network, we can like contract it once in the pre-processing steps and just reuse these numbers in different steps. Okay, so that was a really brief description onto how the algorithm works, because when we talk about limitation of the tensor networks, we really mean it. That is, that is really like cutting edge stuff here used in the tensor network approach. And here is just the taste of the whole stuff we are doing here, because I think we use almost every optimization known to the man to use it to calculate these like really big systems that we have here. And now I want to talk you about some additional optimization we have in our algorithm. First of all, is rotation. Because as you can see from here, we are going in very, just in one direction. And also I want to mention that the contractions we are going here, they are approximate. We are not contracting the tensor network exactly, because then we are just solving even harder problem that we started with. Because reminder, to contract PEPS network exactly is sharp P problem, which is harder than the MP hard problem that we started with. So we are using approximate contractions, so that way, so we can solve this problem. That is important. So when we are going here, we are going in very specific direction, building this model. But because we are using approximation here, we may introduce some biases here. That's why we have methods just to rotate these tensor networks in all their direction by 90 degrees and time and the reflections, so that we can like eliminate the bias introduced by the order in which we are building our solution. Second is sparse network tensor structures. I didn't talk about it in the details because, to be honest, it is quite complicated. But the general idea is presented here. General idea is presented here. That instead of keeping these big, I mean really big tensors, because still even after the projectors we have like 2 to the 80s rows or columns in these matrices, which are still quite big instead, and infeasible in reality to calculate and keep them in memory. Instead of like keeping them as they are, we are like breaking them further apart and use some special optimization so that we can keep them like do not lose accuracy, but also keep them smaller and more manageable. And also, before even we start, we introduce loopy belief propagation, in which we are somewhat heuristically cutting the number of states we are considering. The details are in the article, but I just wanted to give you the taste of the method that we built here. And now the most interesting part, the results. Because, okay, I talk for almost an hour about what we have done, but was it any useful? So how we tested that? Generally, I will show only class 1 instances here, so-called. which are native instances for the given QPU, and which we have no external magnetic fields. So HI is equal to 0. And the coupling strengths are at random, taken uniformly from -1 and 1. This is a simple class of instances we have taken, benchmarked, and they are native for the given QPU. That means there is no embedding there, and they have exact shape of the given quantum processing unit. So that is instances. And here we have, oh, I see some question in chat.
Okay, we have no. If you don't mind, I will read the question, not from me. Can you read it, please, and answer it? You can see it. Yeah, because now I use a good microphone, but without screen. So sorry.
About okay. About the rotation. So the short answer is that the system is not rotation invariant. It is, and that is because of the my pointer worked again. That is because of the way we are also contracting the tensor networks. Because maybe the Potts-Hamiltonian itself is rotation invariant, but when we start contracting the tensor networks, in the heuristic method we are using, the order of contractions matter. So that's why the order in which we build the solutions also matter. And I hope that answered this question. I mean, that's why the bias, in reality, the bias is introduced here during the contractions. Okay, I have answer. And again, the laser pointer stopped working. Okay, so what metrics we use for the benchmarking? First was the quality of solution. That is just the relative difference between the best energy that we found for the given instance and the energy returned by the solver. That would be used. And because we tested many different instances. And second is the diversity of solution. Because, as I said, we are not only finding some low energy state, but also we are sampling from low energy spectrum. And so building our software, we introduce additional feature of finding so-called droplets that are region of the local excitations above the ground state. And we are interested if we can find the solutions that are not only close to the ground state, which is represented by so-called approximation ratio AR. That is, the relative energy difference must be lower than the approximation ratio, but also so-called relative distance threshold. That is this number R, which is between 0 and 1. And D here is the distance between two configurations. For example, we used Hamming distance between two configurations. And we want that the distance between, and big N is the size of the instance that we use. So we want the distance between two solutions. We call them diverse if they are close to the ground state and different from each other. When by the difference we mean they are they have relatively big Hamming distance. Okay. And what do you compare themselves to? First, we compare ourselves to the D-Wave commercially available quantum annealers, of course. Second, when it was possible, because all the calculations were performed on the consumer-grade computers. We didn't use supercomputers for the calculations. We wanted to be sure that it can be run and benchmarked on the consumer-grade stuff. So that's why not all problems were able to be tackled by the CPLEX. And also we compare ourselves to the simulated bifurcation machine, which right now is the state-of-the-art physically inspired solver, and like the greatest available now. Just to be like really clear, we really expect to be beaten by this solver. And here, I will show just some of the solution for the class 1 instances. And okay, this plot may really look complicated, but what do you wanted to show? The orange and gray ones are the results obtained by the D wave at the annealing time, respectively 200 microseconds and 2000 microseconds, where 2000 microseconds is the maximal time we can use on the D wave. This is maximal annealing time, this tau A, which is the annealing time. The dark blue one are simulated bifurcation machine. Green one is our solution, like without additional, like clear, without loopy belief propagations. And then the red, blue, purple, not purple, pink, and brown are our results. But when using another question, yeah, I want to answer it now. Do you know the ground state a priori? We do not know the ground state a priori. That's why we are comparing not to the ground state, but to the best energy return that we found for the given instance. I mean, for some instances, like for Pegasus, okay, and another also for the distance. Okay, when I use distance metric, this distance is not from the ground state, but it is comparison between the two solutions that will return that we have found. Because we are considering two solutions that are, as I said, relatively close to maybe not the ground state, we're relatively close to the best energy we have found, and different enough. And also that here, when we're measuring quality, this E-best is not the ground state because we often cannot certify it, but it is the best solution that we have found within a given problem, yes?
I have a question about the best energy. It is respective to the different approach used, or
Yeah, different approaches we use.
Yes, so it's different best energy for different.
No. We look for the best energy found by the different approach, and use the best one overall found for the comparisons. Because, as I said, we cannot certify it or found the ground state. So the best we have. Okay, let's see. One message. Okay. And the number of solution is defined by, okay. Generally, in our method, we can specify it if we want. As I said, in the branch and bound method, we kept M most probable states, and this M can be set by us. And also with the simulated bifurcation machine, we can also set how many solutions we want to find, because as physics-inspired solver, okay, maybe I won't go into the details, but also Stplex only returning one solution. And the simulated bifurcation machines, also we can set how many solutions we want from the given solver. And that why we are not interested in the number of solutions, because we can specify it, but in the diversity. That is, the solutions found are not only close to the best we found, but also diverse. That is, far apart in the terms of the Hamming distance. I hope this answered the questions. Okay, so looking to it, the first row is 3 different classes of Pegasuses. We look into it with 216 spins, 1000 spins, and 5000 spins, where here is the full Pegasus. And on this, we have time in second, and it is logarithmic scale, and here is this relative distance that we are interested in. And as we can see, for the small instances, our method takes a really long time, but it also finds the best solutions that they are like this, similarly to the simulated bifurcation machines for like the solution for the different time we used, as you can see. But for the bigger problems, we are not only taking really long time without like these additional optimizations, and also like even D-Wave can for these small instances, even D-Wave can find some solutions. But here, as we can see, we are not only this method is not only finding it's taking long time, but the solution quality is not so good, as we can say, and as we can see, we are firmly beaten by the SBM, which we expected. And here, and also the D-Wave is giving us like comparable quality of solutions here. But what is interesting for the full Pegasus, we had to use the loopy belief propagation here because we cannot calculate them exactly. Here also SBM is best. And here we are obtaining similar results to the D-Wave. And here are the results for Zephyr. And also, as we expected, the SBM is the best. It's beating D-Wave, beating everything. So here the results are not so promising for at least this class of the instance. Here we are solving the diversity of solution, and just to be quick, the generally here the higher number is better because we are like seeing like the mean solution diverse enough that is with this approximation ratio 0.01 and the threshold distance 1/2. That means at least half of the spins in the different solution have to be different to really call them the diverse solution. And here also the SBM and the D-Wave are giving us the most diverse solution here. They're different, but generally for bigger instances, we are getting better, especially for Zephyr. And for the Zephyr, this is orange, if I remember correctly, we are getting better solutions for the most diverse solution than the D-Wave. Okay, so that doesn't look really promising. And also there's a problem, but also we have looked into the another class of instances because we can. So instead of native instances, we looked into the square lattice with the diagonal connection, and with here is 50 by 50, which is I think around 2000 spins. And here we have the square lattice with one spin on each lattice side with diagonal connections. And here we compare also between CPLEX and SBM. And we didn't have to use any this loopy belief propagation because we could take this instance as we want. And what is interesting, and also we didn't compare also to the D-Wave because the D-Wave cannot solve these instances. They are too big from him. for him with this connectivity structure. For these instances, we are getting better results than the simplex, than the SBM algorithm, which is surprising. We didn't expect that there will be any instances that we are better. And also, we are getting solutions similarly diverse. And the same is for square lattice with diagonal connections, but now we have two spins on each side, in which, and here like SBM is better than us, but we are still beating a simplex. Because here we have median values, here are the values for each of the instances we tested. And here is diversity of solution. And of course, the simplex are not giving us the diverse solution because it is returning only one solution. So no diversity here. But showing it, and this is only the part of the solution of all the benchmarking, because in the paper we have done much more thorough benchmarking of the everything, and we show the another classes of instances, and there are another classes of the instances when the tensor network are performing quite well. But I wanted now to focus on some conclusions about this work, because this work was not really about how awesome this tensor network approach is for this problem, but what limits we have crashed into. That is, first of all, is performance trade-off. That is, there are cases when when the tensor network can get really good quality solution, even state of the art, but we are paying for this with the computational time, because they are really expensive to calculate. Second, the sampling limitations. It is the same problem, that even even though we can set the m most probable solutions, they are often quite close together. And also, that's why also like they are really expensive to calculate. And I think the most important and damning thing is the scalability and stability. That is, because also in the paper, we are really thoroughly benchmarking the stability of our solution and the stability of calculations. And what is important, the tensor network, this method, and general PEPS tensor methods are scaling really badly for big optimization problems. And that means that the time to solution is increasing really quickly, with the still sub-exponential to be clear, but it's still quickly increasing with the size of the problem. That means I don't think there will be tensor network solvers for optimization problems with, I don't know, 100 variables. Okay, so the limitations, there are some limitations for optimization and sampling. So why would we even use and care about these tensor networks? Because we can do much more than just optimization and sampling. But tensor networks are generally a great tool for performing simulations of quantum many-body systems and other complex systems. And that's where they shine. Like, for example, okay, here is literature I have used. Our main paper, which are based this talk about. And another paper, which is going into the software part of our method. And thank you for your attention. And here is the link for the interactive demo of our software, which I will show. But I want to stress that I will talk about it when we go to the software, again, with software feature, but I want to stress that tensor networks are best used for calculating physical properties and performing physical simulations of many-body quantum system. Or, I mean, that's the use case I'm most familiar with. But there are other use cases, for example, for big data analysis, etc. So that is their use case, and was great successes with these use cases. For example, the classical models were generally there is this discussion going with D-Wave and quantum annealers how good they are for simulations, and the tensor network community generally is showing that almost everything that can be done by the D-Wave in terms of simulations can be done better by the tensor networks. And it is really interesting discussions here. And I want to stress that they are interesting. And that's why this talk was titled The Limitations of Tensor Networks and not how great are tensor networks. Because in this research, when we started, we didn't know that. But in this research, we really crashed headfirst into we think there are some real fundamental limitations of these methods, at least for optimization and sampling. And optimizations might be not good use case for tensor networks. Okay, so thank you for your attention. And now I will go to the interactive demo. Any questions so far for the theoretical part?
So thank you for talk, and so it will be in the way that we have now some time for questions, and then we'll go through the demo, right? Yeah. Okay, it's okay. So there is some question here. I will. Okay. Oh, sorry. Can you open it?
Yeah,
oh, I'm sorry. Sorry. So how many? Well, I think it's better for you to.
Yeah. Yeah, I think it is not really important how many solutions we requested. I think it was around 1,000 for each run, and 1,000 solution. And for each run of the tensor networks, we perform full 8 rotations to find a solution. And I don't think, because in our software we can also set up the limitation, so-called the largest probability that we are accepting. So for example, we can set that we want 1,000 solutions, but for example, 500 of them have so low probabilities that to save time, we are just throwing them away anyway. And this all can be set in the solution, in the software, which I will show later in the demo. But in general, the performance here is shown from, as I said, we perform all 8 rotations and reflections for each of them. Because I want to stress that we have seen not only quality of the solution, but also diversity. That is, if the solutions are different enough that we are interested in them. Not only that they are like different solution. Because it can be easily shown that when we have low energy state, changing 1 of 2 spins also will give us low energy state, but they are like computational optimization is conversion of solution is time. Yeah, in general, the number of solutions is, I wouldn't say it is time independent, But in general, yes, we have probability cutoff, then the number of solutions stop being like important part of the time to perform calculations. It can become almost time independent, yes. Okay, thank you for your questions. Any other question?
Yeah, I have a question. So you propose some benchmarking method when you sampled your Ising model. Then you are using this coupling that were uniformly distributed. So my question is like, what is your knowledge about the distribution of the results? Of the distribution of the energies for such a random model. For example, if there will be like a heavy tail with many results that are concentrated nearby the ground state value, then probably many methods would work good. But if there will be like some spectral gap, not only between the ground state, but also between some states that are nearby and with the more solutions, right? Then how in that situation the tensor-network approach could work, and also other proposed like machinery that you were mentioning.
Yeah, that is actually a very good question. So first of all, now here I'm only shown that for the uniformly distributed instances, but we have also tested on the another classes of instances. For example, corrupted biased ferromagnet for Pegasus, which is a heavily biased instance and not at all uniform. And we have got like similar results that the results were consistent around different classes that we have tested, at least for the native instances. And as far as I know, if we use the uniform coupling, we will have somewhat, because of the convergence theorems, the older instances are quite similar, and they have they don't have heavy tail, as far as I remember correctly. They are quite nicely distributed, at least in the low energy spectrum, at least in the low energy region, because this is also the problem with the Ising model itself, and the problem itself that it can have the number of local minimas is increasing exponentially with the number of the spins. So not only we have exponential number of solutions to check, but also we have exponential number of local minimas. That is why many methods are getting stuck there. Also, tensor-network method can be stuck in the local minimas, but as far as I remember, because I have checked it, like it was several years ago when I checked the distribution of the instances. There, if we use uniform distribution with the coupling strength, we get somewhat uniform distribution of the energy spectrum without heavy tail.
Okay, thank you for your answer.
Okay, so now I will go into the, okay, stop share, and I will share a new one, the demo. Okay, so first of all, the software was written in Julia. So to even run this demo, we have to install Julia. And here is the instruction how to do it. You go to the Julia downloads site, you install the appropriate installer for your operating system. Julia supports both Windows, Linux, and Macintosh. We can add Julia to the path variable. This is optional, and how to launch Julia? Generally, it is quite easy. If you okay, I will take this here. And what is important from the system with Windows, we have to use not PowerShell, but command line. So assuming that Julia is installed, it can be run by just typing Julia into the command line. Okay, so here we are in the Julia operating system. First, what we have to do is to install the iJulia package, which is used to, we have to use it to install use Jupyter notebooks. And it can be done in two ways. We can either in Julia type using pkg and pkg at Julia, or we can press the it is the right square bracket, which then goes into the package manager in Julia. And here we can just write add. And it will download and install the package. And what is important here, what I'm showing here is like building this package for the main environment, because I didn't wanted to clog this demo with instruction on how to build your own virtual environment, etc. So we have to wait some time to everything will build and precompile, and I hope it can be seen on what is happening right now, that also I wanted to show how to build it and to go from the zero empty Julia installation, and not just show with everything set up and just click run. Okay, so when we installed iJulia, only thing left is to install the SpinGlassPEPS package, and it can be done the same way. Just writing add and not spin. Of course, I can type. Okay, and when the package is installing, I will show you how this package works. There's something wrong here. Oh, Markdown, and why it... Okay, okay. So when everything is installing, I will show you how the package is built. What is the general idea? As I told you before, we have three problems to solve. That is how to translate the Ising model into the format good for the tensor networks, the perform branch and bound, and how to perform efficient tensor network calculations. And this leads us to designing SpinGlassPEPS as the collection of three different packages: SpinGlass Networks, SpinGlass Engine, and SpinGlass Tensors. And each of them have their own role to perform. First of all, SpinGlass Networks.jl is somewhat independent package that is translating the Ising problem we give it to it into the Potts-Hamiltonian that I showed you, this format that is readable to the tensor networks. And this is the first input we have for our software. The second input are just the sampler and contract options that we feed to the SpinGlass engine, which is the main package of our SpinGlassPEPS, and which is the performing not only the creation of PEPs, contractions, but also the main branch and bound search. And the third package is SpinGlass Tensors, also independent back-end package, which performs all necessary tensor network operations. And that is how the SpinGlassPEPS is built as a software with this free independent package. And at the end, we get the output file, which is solution. And what I want to stress, the package features is not only solving this Ising or QUBO problems. QUBO is quadratic unconstrained binary optimization. And it is just another mathematical formulation of the Ising problem. We also can sample from low energy spectrum. And we can also perform so-called droplet discovery. This is the term from the solid matter physics. And general idea is that we are wanting to see some specific localized excitation above the ground state of above some low energy state. We cannot find ground. And also, what I also want to mention now, as you can see, we are building the Potts-Hamiltonian there in the SpinGlass networks. But it is not like completely necessary. That is, we can also feed our algorithm we can like remove the step and just to present Potts-Hamiltonian to our methods, to our algorithm, which allows us to solve any problem which is like shown in the way of the Potts-Hamiltonian, which is, for example, color segmentation, image in painting, etc., which I will show in the examples. We can do something more than just solving the Ising or QUBO problems. Okay, I hope that the stuff is installed. Yeah, it is. Okay, the packages are installed. So now I will go through the basic example, and it should be Julia. Okay. And I will go step by step of this big block of code. First of all, we define this get instance functions, which is just reading the instance from the file. Nothing interesting here. I'm sorry. What is important it is that we have this topology parameter that is defining the. Okay, it's not important. It's just defining the shape of our instance, and we use this as the useful way to read our instance. What is important is this part, defining the Hamiltonian, which is here and that. Okay, so first of all, when we are defining Potts-Hamiltonian, that is the step which are shown at the beginning, which is translating the Ising model into the Potts-Hamiltonian. What won't we do? We have to feed it this Ising graph with instance. The spectrum with full spectrum, we can think of it as default parameter, but here it means that we are not performing loopy belief propagations. We are just taking it as it is. And the cluster assignment rule, that means this is the functions, or more precise, the dictionary, which tell us how are we grouping the spins together. If you remember from the presentation, we were grouping all spins into the spots variables, and here is how we are doing. And super square lattice are taking us that we are taking the square lattice of diagonal connections with several spins at each lattice site, which was shown here. This is what I mean by super square lattice, that we have lattice with diagonal connections. And at each lattice side, we have several spins. Okay, so here we create a post-Hamiltonian. Here we are setting the parameters that are shaping our search. And as I said, our software is really, really configurable. That means there are many parts that we can specify or change during the search. And these are just several things we can set. For example, bond dimension. That is the maximum number of bond dimensions of the tensor network that we are use. Number of sweeps. This is just number of sweeps we do during the contractions, which is called here variational compressions. Max state. That is this M that I called. The maximum number of search states we are keeping during the search, and the cutoff probability, which is that the probability with below which we just discard the states, even if they are like still below the maximum number of states. That is the second parameter, which is that is how we search. We are setting it here, and then we are just building the tensor network with several additional parameters that we can set here. We can we can set how the nodes are built. We can add gauges, which is additional advanced feature. We can specify if we want dense or sparse tensor structure. And to not bore everyone, in general, think of it that we have the code looks somewhat complicated because it is really customizable. I mean, the main goal of this package was not to give people a good solver. I mean, it is good solver, but it is that was not the point. The main point was to reduce the barrier of using advanced tensor network methods. That is, we have implemented all the hard stuff, all the hard contractions, or the GPU accelerations, everything that is needed, and we are letting the user manipulate many different parts of it to use in their own project, own research. That's why there are so many options, there are so many steps, because everything can be changed. Everything is configurable. And that was the main goal. That's why it looks somewhat complicated and it isn't just like solve one function. We have to set many things because everything can be changed. Okay. So we have, then now we have how we find droplets. Here is we define another options, how we are truncating tensor networks. You are doing it on GPU or not, value of beta, graduate truncation also is another advanced parameters. How we are merging the branches. That is the strategy. It is important for the droplets when we are, as I said, reducing the number of states we are considering because of these boundary conditions. And what is important, beside the solution, which is really big like structure, which is not only getting the states, we are getting the droplet, we are getting maximum discarded probability, we are getting energy level degeneration and the generation analysis. We are also getting the Schmidt spectra for the created PEPS network, which is also like another concept which I didn't have the time to mention. And this is just the function of low energy spectrum. This is our main function, which will give contractor, parameters, and merge strategy to it. And then the rest is the boilerplate to unpack everything. And kernel source, of course, I cannot see it. Julia. This one. Okay, let's hope it works now. Now I define these functions. everything. And after telling you everything, I can show you. And also, of course, we can specify what kind of float we are using or our calculations. And we also checked it in our paper if there was difference between using float 64 and 32. And for some reason, it isn't printing me the solution I want. Okay, I will do it the classical way, because the Julia in the Jupyter Notebook works somehow better or worse. So I will show you how to do it on the just running the similar Julia files, but for the Pegasus. So where am I? Demo. Julia include, and this is Pegasus. Okay. Now we are running this demo here, shown in this is the same similar file, but it is taking the Pegasus instances with 200 spins. And now we are doing some pre-compilation process because Julia is a specific programming language that is compiled, but it is they are promoting it as a language that is so easy to write as Python and as quick as C. And in practice, it is easier to write than C and much quicker than Python. But still not as quick as C and not as easy as Python. And this can take some time. Maybe I should precompile everything later, but I wanted to show you the full experience of using Julia and packages, because it is an important step, because it is done only once after installing your packages. It's precompilation, but it is important to show it that to like another user won't be scared about what is happening now. And also important to remember that I am running it on my very small and very not very powerful laptop. So for normal users, it should be much quicker if you use like real computer and not like laptop for presentations. And of course, when I was checking it yesterday, it was much quicker. But like I see, maybe, yeah, my laptop is getting hot. Yeah, Zoom and everything, yeah, and this is slow, because I can tell you that when I checked it yesterday, that to be sure that everything works, it was much quicker, and I was quite happy with my results. But now we crashed into the machine spirit. But still, I have time till 3 p.m. So yeah, we can all wait here. But what is good, as I said, this preprocessing only is take once. Yeah, and these are the some stuff that are left after the previous compilations. Because of course I compiled everything and then removed the environment to be sure that to show everything from the blank state on the presentation day. And also, okay, I want to show one important stuff, that our software also is supporting both GPU and CPU calculations. But is, as you can see, it is just simple. We checked if it has the GPU, and then we can just pass it to the function if we want GPU or not. Here, in the contractor, we can specify if we want to calculate on GPU or not on GPUs, and if not GPU, and then we will use CPU for calculating. And I don't trust my computer that it will manage today. But general idea here I wanted to show you, and what I wanted you to take away from this presentation is that, and from this little demo, that although we can take long time to calculate stuff, because it is not the quickest software, we can do great things with it. I mean, it is really configurable. It can be used and built upon and easily, like it's really modular. You can easily take one part away, substitute for other, and it should just work. And that's why it may be complicated, but because of that, it can be used in another like research project. And also it is designed to work with the quantum annealing architectures, which later can be built, like, for example, to calculate some thermodynamical properties, etc. It all can be done here. Relatively easily. Thank you. Sorry. Okay, like, I can tell you that I'm not satisfied with my computer. Yeah, I hope that some people up there clone the repository from the GitHub and are running it on their own machines, and they are seeing results right now. Okay, maybe I won't be stopping you here and ask you about any questions to the software part. Okay, so maybe I will show you everyone the link to the demo again, and I won't be keeping you here waiting. Thank you for your attention, and I'm sorry that my computer break during the presentation.
So thank you, Tomasz, for a nice talk. Next seminar, quantum computing seminar, will be in September, and it will be announced as it's not decided yet. And with this, I would like to thank you all once again for your attention, and see you later, maybe. Bye.